This is the pre-lab video for the second week of the copper complex lab for Chem 111. Recall that we are determining the chemical formula of the product that you synthesized last week. And the basic formula for that is copper. We have some amount of copper, and the X, Y, and Z and A are all integers. Okay, they are mole-mole ratios of copper and ammonia and sulfate ion, and as well as this is a hydrate, so we have some waters in there. So these are integers, and we need to figure out what the mole-mole ratio is so that we know what these integers are, and therefore we can determine what the formula of this compound is. So when you come into lab this week, you will measure the mass of your dry copper complex. This is the blue stuff, okay? So this is the blue. You'll have to subtract your filter paper and your watch glass or your beaker. I had my students put it in a beaker. If you forgot to get the mass of your beaker, it's okay. Get the mass of your beaker with your product and your filter paper. Record that in your notebook. You can then put that into something else, okay? Put it into another beaker and wash out your beaker that you used. Wash it out, dry it completely, and then you can get the mass of that and subtract it. So you need to get the mass of your product isolated and record that in your notebook just like that, because there will be a place for that in your lab report form. You also need to record the mass of your lead sulfate. This is what is in this is the white product that is in the large filter paper. So again, you will need to get this mass and subtract off the mass of your filter papers. This is the first page of your report form, and I'm going to keep coming back to this several times during this video, but I want to just keep things clear of where you need to record things. So this is your sulfate determination. This is part B of what you did last week. And you did part A here. So you used a certain mass of copper sulfate. This is about 10 grams here, okay, 10 grams of copper sulfate pentahydrate. Mass of your product isolated. This is what you're measuring this week. Okay, so subtract off your filter paper and your beaker, and this is where that mass of your product isolated. Another way of saying it is this is your actual yield. Right here is where you will record your mass of your lead sulfate that you just recorded. This week, we will be determining how much ammonia we have in our complex as well as copper. So I'm going to address the ammonia first. You will use your blue copper complex compound for the ammonia analysis. Last week, we used what had already been synthesized in previous semesters, but for what you do this week, you will be using your compound. For the determination of ammonia, we will be performing a titration, very similar to the molar mass of an acid titration that we performed a couple weeks ago. This time, though, we will have the ammonia from our copper complex. We will be adding an acid, okay? So ammonia is a base. We'll be adding an acid, and it's HCl. This is what's in the burette. Your HCl is what will be in your burette for your titration. And this is the equation that happens. You will weigh 2 samples of about 1 gram each of your copper compound to the nearest 0.001. It does not say how much to use in your manual. So this is something that your lab instructor could ask you to find out if you actually watched the video. So put this right in your lab manual right now, that you need to weigh out 1 gram of each for your ammonia. Because guess what? If you ask your lab instructor how much to use, they will know that you didn't watch this video. So make sure you write that down. 2 samples of about 1 gram each. Dissolve each in about 30 milliliters of water. As always, don't use tap, use the purified water. And an Erlenmeyer flask, recall, is the one that looks like this. And you want to do your titration quite quickly. You're going to be using methyl orange as an indicator, and it goes through a series of color changes, and you'll end on one that's kind of a reddish orangish color. But what you really should be looking for in addition to that is that there is a solid in there that will disappear just before the end point. Make sure you record the molarity of your HCl. Okay? It will be on the bottle that you use to fill up your burette. Make sure you write that down because you need it for your calculations. You need at least 2 good trials of the titration. Okay, how do you determine if they are good? Well, the ratio of the volume of the acid that you use. So recall that when you measure your burette, you have an initial volume and a final volume that you read. So you subtract those. That's the volume of acid that you used. So you divide that by the mass of your sample, that's your copper complex mass. Divide those. Compare those ratios. If they agree within 1%, you're done. If not, do another trial. This calculation sample is in your manual. And this lab is wonderful because it gives you the sample calculation for everything that you need to do. And the top of these boxes give you the mass and volume, basically the data that you collected in the lab. So you should have the mass of your copper compound that you used for, say, trial 1. This might be trial 1. You should be performing your calculations for each trial to get to % ammonia. Please do not average your data together and then do one calculation. You do the calculation separately for each trial, and then you can compare and perhaps average your results. This is the volume of HCl that we used in our titration. This is your burette readings, final minus initial. This is an error right here. This is supposed to be liters. If you change 30 milliliters into liters, you get 0.0303 liters of HCl. This molarity, 0.512, is what you read off the bottle. If you multiply these together, then you have the moles of HCl. In our balanced equation that I gave you here, you can see that it's a 1-to-1 ratio of ammonia to HCl. So moles of HCl equal moles of ammonia. Then you can convert your moles of ammonia into grams. You know how to do this. You can just multiply by the molar mass of ammonia. Now we have grams. This is the grams of ammonia that were contained within the mass of sample that we measured out. So to get a % mass or a % by mass of ammonia in our original compound, this is the mass of ammonia, our part, divided by the mass of our entire sample, that's the whole, times 100. So this is the % ammonia in our sample. And that's what you want to get to. Do this for both trials, and you will end up with a % here. Now, you might have needed a third trial. Take a look, okay, calculate it for all of them, but just average the ones that agreed within 1%. So you might be averaging these two, or you might be averaging these two. Depending on which ones agreed, average those. And you need to, in your report form, perform that calculation and show the sample mass calculation. You only have to show one. Okay, back to our summary sheet. This is the first page. Now we are doing this. Okay, so this is week 2. Concentration of HCl. This is right from the bottle. Okay, it's about 0.5. Okay, but you should put in what it actually is there. Mass of sample used in your volumetric analysis. These are your samples of your copper complex. It's going to be about 1 gram for each of those. Volume used in your titration. This is final minus initial here. And then your average. This will be one number, your average % of the NH3 of your 2 trials that were close. So now you have an average % ammonia. You also have an average % of sulfate. That's what you calculated. The first video showed you how to calculate that. Okay, so you have both of those. Now we need to figure out how much copper we have. We're going to do a spectrophotometric analysis of copper, very, very similar to, almost identical to, the copper analysis that we did last week. So similarly, we will be using the burettes that are set up in the hood, and you will have used 6 different test tubes. Okay, these are the larger test tubes that are in your drawer. The first one is your blank. Okay, this is your blank, so you can just fill your cuvette with 1 molar HNO3 or nitric acid. Okay, in test tube number 2, you will have some copper solution and some nitric, and you're going to measure that as precisely as you can. And then also a mixture for tube number 3. And then this is straight up copper from the copper burette. you want to write down what the molarity is of your copper. It might be very close to 0.015 molar. Okay, write that down somewhere because your tube number 4, that's the concentration of tube number 4. For 5 and 6, you will use your copper compound or your copper complex that you synthesized. The first one, you're going to measure out approximately 0.2. The second one, you're going to measure out approximately 0.3 and dissolve it in exactly 10 milliliters of nitric acid. So now you have 6 different test tubes. You will fill up 6 cuvettes and measure them on the spectrophotometer. So here's sample data of the absorbance readings for each of these test tubes. So the first 4 are of known concentration. The concentration of tube 1 is 0. The concentration, so I'm going to put molarity here. The concentration of tube 2 was, okay, we're going to use M1V1 equals M2V2 to figure that out. So we had 4 milliliters of, let's say it was 0.15 molar copper, and we used 4 milliliters of it. That equals, this is M1V1 equals M2 is what we're looking for. What's the molarity? Times 10 milliliters, because that was our total volume. We had 4 milliliters plus another 6 milliliters is 10. Okay, so that's how you solve for molarity of test tube 2 and test tube 3. Test tube number 4 is 0.15. Okay, we gave you that. Test tube 5 and 6, we're going to have to do a calculation to figure out what those concentrations are. But we know the first 4 concentrations, and we will use those to make a standard curve. Just like last week, you plot your concentration, copper concentration versus absorbance. Okay, that's just 4 points. Make sure that Excel gives you the equation for your trend line. Add a trend line. It should be nice and linear. Your B or your y-intercept should be 0 or very, very close to 0. And then you'll have a slope. Any additional absorbance value that you measure for copper, once you have this relationship, you can say, okay, if I get an absorbance of 0.4, then this relationship will give me the concentration. So if I know another y, I can solve for x. And that's what you're going to do with the absorbance value from test tube 5 and 6. So for example, your absorbance of 0.39 for test tube 5, you can plug into this equation for y and solve for x. And that's what this is doing. And you can see how we have y minus b over m is x. So this is just rearranging that equation. Don't be confused by this. Plug your absorbance in for y and solve for x. That gives you the molarity of your copper in sample test tube number 5. That's in moles per liter of copper. So in the next step here, this is moles per liter. If you multiply moles per liter times the number of liters that we had, and recall that we had a total of 10 milliliters, so that's 0.01 liters, times your molarity gives you the moles of copper, and you can see there's a little typo there. We don't need those extra 0 point there. So 0.00803 moles. Now we have the moles of copper in our test tube. Well, how many grams of copper is that? So you just multiply the moles by the gram formula mass. That's right off the periodic table for copper. So copper ion is the same mass as copper atom. Okay. The fact that we lost 2 electrons did not change the mass, so it's still 63.55. Now we have the grams of copper that were contained within that test tube. So the part over the whole gives us percent. The mass of copper over the total mass. Remember that your mass of your test tube number 5 was in the 0.2 range. In this example, it's 0.215. So this will be your mass that you measured for test tube number 5. And it gives you a percent. So this is your percent copper for test tube number 5. You would do the same calculation for test tube number 6, okay? And you'll be be able to compare these percentages. So in your report form, you have this. You have to fill out your molarities, okay? And you did this with M1V1 equals M2V2. You got your molarities. This is your 0.15 or your 0.16, whatever it is, right off of the burette, and your absorbance readings. Same for sample 5 and sample 6. So you calculated your percent mass of copper for both test tubes 5 and 6, and this is your average. Your average then goes right here. Now we have a percent copper, we have a percent ammonia, and a percent sulfate. In your report form, though, you have to attach your graph, okay? Make sure you attach your graph to your report form. Put the equation for your line here, your y equals mx plus b, and show a sample calculation that I just showed you for your data. So now we have this mostly filled out. Okay, so we have all of this filled out so far. So how do we do the rest? Putting it all together. We need to figure out what the formula of the compound is, right? So that's what you will use this chart for. If you assume that you have 100 grams of your sample, those percents by mass that we figured out for copper, ammonia, and sulfate turn into grams. So 23.74% is now 23.74 grams if we assume 100 grams. We know how to turn grams into moles, right? So grams divided by your grams per mole gives you moles. That's how you come up with this column. For example, our 23.74 grams of copper divided by 63.55 grams of copper in 1 mole gives us our moles of copper. You do that for your ammonia, you do that for your sulfate, and you also do it for water. Well, how did we get the water? We have a total of 100 grams assumed here. If you add up your copper, ammonia, and your sulfate, and you get some number, it should be less than 100. Subtract that from 100, and that's what's left over, and that's what we're assuming is the water. So you can also turn your grams of water into moles of water. So you have a moles of water piece, moles of sulfate piece, moles of ammonia. If we have our moles of each, we can get a mole-mole ratio if we divide by the smallest one. So recall, this is getting an empirical formula from your percent masses. We're telling you that your smallest one should be copper. So we're telling you to divide each of them by the copper moles. That will turn this ratio into a 1. Okay, if you divide anything by itself, you get a 1. Now, hopefully, each of these will turn out to be whole numbers. If they do, you just put them into your formula, right? So this is your moles of copper. That's your subscript for copper. If they're not whole numbers, you will have to do something to get them to be whole numbers. So, for example, if y turns out to be 1 and z turns out to be 1.5 and a turned out to be 2, we have to turn this decimal into a whole number. So a 0.5, if we multiply that by 2, then we could get 3. But these are all ratios. We have to maintain these ratios. So if we do it to 1, we have to do it to all of them. Okay, so that would be a 2 to 2 to 3 to 4 ratio then for this example. This is in your report form. So here's your general formula. So you'll use your whole numbers that you get from that table up above, and you will write the formula of your compound here. So in my example up above, if I had 2 to 2 to 3 to 4 ratio, I would have to write copper 2, and H3 2, SO4 3, dot 4 H2O. Molar mass, okay, that's gram formula mass of the compound. So for your formula, you need to figure out the molar mass of the compound by just using the periodic table. And this will be a pretty large number. Mass of your copper sulfate pentahydrate used in the synthesis, that was the mass that was about 10 grams. Okay, so that was the initial mass of copper sulfate that you used in your synthesis. This is important because this is our starting number to calculate our theoretical yield. Your theoretical yield, you start with your 10 grams or whatever your actual number is. Let's say it's 10.015 grams of your copper sulfate pentahydrate. We can turn that into moles of copper sulfate pentahydrate, and then we can turn it into moles of your copper complex. The mole-mole ratio of the sulfate down here to your compound, this will be 1 mole of copper sulfate to however many moles you have in your compound. So for our example here, this is a 1:2 ratio. So now you have moles of your compound, and then you can turn that into grams of your compound because you have your gram formula mass. So this amount of grams comes from here. Grams per mole of your compound. That gives you your grams of the complex, which is your theoretical yield. That equals your theoretical yield. Mass of product isolated is your actual yield. Calculation of percent yield is then actual over theoretical times 100%. So if we go back to our summary of results here, you put your formula of your compound here, your theoretical yield that we just calculated, and your percent yield, and you are done.